Hello everyone. In this video, we are going to look at some of the essential features of commutation in a DC machine. So when you say commutation, it is basically the current reversal. The current reversal happens in a coil by means of the brush and commutator arrangement. And to make it little simpler or easier, I can say that in a armature coil, we know that the current in the coil undergoes the change in direction with respect to the changeover in the direction of flux, but at the same time we would like to retain the current direction at the given brush in unidirectional. So to make this current to be unidirectional at the exit point of the brush, we are using the process of commutator. So when it comes to the process of commutation, people used to call the commutation process is good or poor. They would like to verify. When you say the commutation process is poor, there is a chance that there is a sparking at the junction of or at the meeting point of brush and commutator. This is what generally named as a poor commutation. So if there is no sparking identified in that particular location, then people used to say that the commutation is a good commutation, or the commutation process is good in the particular machine. So you may wonder that what causes this such a poor commutation. What could be the reasons? The reasons may be like, there is a chance of an uneven surface. If there is an uneven surface of commutator, naturally there is a chance of sparking. It is kind of due to the friction between the brush and the commutator contact. And there is another one, the contact pressure on the brush may not be it may not be uniform, or I can say it is non-uniform. What do you mean by the contact pressure on the brush? See, we know that when the commutators keep rotating, and the brush what we use is a carbon brush, so there is a chance that the carbon brush, due to the friction, it may get lost. That means the thickness of the brush may reduce due to the erosion. So when such reduction in the height of the brush happens, there is a chance that the uniform pressure given on the brush may not be possible. Then there is a chance of vibration, due to some vibration that may happen due to various reasons. The vibration may come from the armature shaft, or it may be coming from the brush holder. Probably in our physical class, we will be looking at these 2 points, but this uneven surface on the commutator, it is basically due to the copper material used in the commutator would have eroded, or the manufacturing defect itself would have caused some problem. But the point here is that is this only due to the mechanical reason? The all the poor commutation, that means that leads to kind of sparking. Is it only due to the listed mechanical reason, or is there any electrical reason? It is identified that yes, there is an electrical reason behind the sparking comes in the commutator segment. So that let us look at now. So to look at that, let us understand how the reversal of current happens in a commutator segment. The process sorry, not in the commutator segment, in a given coil, how the reversal of current is understood with respect to the process of commutation. That we have to look at. So to look at that, you can look at a figure here. This figure, I think when we developed the winding diagram, you should have seen in a different look, but I have made a slightly a different format of diagram. So what you are looking at is the portion of an armature of a DC machine. That means you can see these are coils. These are coils present in the armature. And we know that the commutator segment, here I marked as 1, 2, 3, in a double layer winding, each commutator segment is getting connected with two coil sides. Two coil sides are getting connected to one single commutator segment. And we have learned about how to position the brush as per the winding diagram. And currently, this particular brush, let us say we are looking at a generator operation, this positive polarity of the brush is currently staying with the commutator segment 1. Okay, and I have marked the direction of rotation. It basically the clockwise direction is mentioned here. So what we are going to do now is we are going to see some snapshot of the motion of the commutator segment along with the armature with respect to the position of the brush. That means when that continuous rotation happens, what are the changes happening in the coil, in the commutator segment, and in the brush. So to look at the entire process, we are concentrating on this particular coil 1, which is one side of that is connected to the commutator segment 1, the other side of that is connected to the commutator segment 2. So our concentration throughout the explanation will be on the coil number 1. So having said that, let me take this figure again, and let me just do a copy paste here. So as I mentioned, we are very particular in terms of looking at the current reversal which is going to happen with respect to coil 1. First, at this moment, let us mark the current directions in the coil. Okay, first let us mark the current directions in the coil. So let us assume that the current from each coil at this time, call that as IC. Call the current flowing through a particular coil is IC. And we know that through our winding diagram, we will be placing the brush where the current direction of the two coils are towards the commutator segment or away from the commutator segment. So with that, I think the current direction in this particular coil is going to be like this. So what we have done, we have just marked the current directions at in all the seen coils in a given instant of time. So if coil 1 offers you a current of IC, so let me, for understanding, let me take coil 2 offers a current of IC, then the current will come out through this commutator segment 1, and the current which is ejected from the brush is going to be 2IC at this point. And let us not forget an important point here, that when you are saying the current which is coming out of the brush is 2IC, we know very well that this particular current is being taken by the load. So it means if you are not changing any load condition at your terminal, then this 2IC is expected to be retained. Don't forget this condition. This 2IC ejected from this particular brush is retained to be constant if at all you are not disturbing the load. So that is another assumption we made. Now let us move further. What we are going to look at in the next immediate picture is going to be that we could see the movement of armature, and because of that movement, what are the changes we are going to look at. So it means that we are going to make this armature moving in the clockwise direction, and when there is a movement, I am just going to change this position of the brush slightly. It means that in this picture, okay, let me call this as figure 1. In the figure 1, the commutator segment 1 is completely occupied by the brush. Okay, that means here the assumption is the width of the brush is equal to the width of the commutator segment. So it is completely occupied. But in the next instant, you can look at how I am drawing. Surely the constructed machine will not have a different size of brush in each instant. So naturally, the brush width is maintained, but you can look at the position change with respect to the commutator and brush. Now, the part of the brush is started getting connected to commutator segment 2, and it is slowly started leaving from commutator segment 1. So at this junction, as I told you, for sure the current which is being ejected from the brush will still retain to be 2IC, because you are not disturbing the load. Okay, so now we have to watch closely that there is a part of current which is started coming from commutator segment 2, and commutator segment 1 still contributes to the current 2IC. So basically this 2IC is partly coming from commutator 2 and partly majorly coming from commutator segment 1. So just for the understanding, let us assume that the part of the current which is being supplied through commutator segment, let us mark that current as say I1. Let us say I1. It is not equal to IC. Okay, it is I1. We can assume that I1. We can assume that the I1 is the value of I1 is less than the value of current IC. Okay, so partly it is coming. So naturally, if this is going to be I1, then if at all that is coming from this particular coil, uh, let us call the current in this coil is still IC. Let me say this is C3 and this is C2. Okay, this is still IC, and if this is still IC, and uh, here the current comes out from this is just we have taken as I1. So now in this particular junction, you can apply Kirchhoff's current law. You can apply Kirchhoff's current law. So if you apply Kirchhoff's current law, the current in coil number 1 happen to be IC minus I1. You look at that. Earlier the current in figure 1, you can call this as figure 2. This is figure 2. In figure 1, the coil 1 current carries I1. Now in figure 2, it is IC minus I1 because the part of the current coming from coil 3 is started contributing the load current, and the contribution from that particular coil is just I1. Then there is a reduction in the current from the coil coil C1. So now we have to look at this branch. Okay, and please remember coil 2 current still IC in this direction. So this particular branch will have, you can apply Kirchhoff's current law here, it will be 2 IC minus I1. So 2 IC minus I1 is the current contributed from or contributed through commutator segment 1. So what is the total current from through commutator segment 2? It is I1, and through commutator segment 1 it is 2 IC minus I1. So it happened to be 2 IC. Now you look at this, we are still getting 2 IC out of the brush, but this 2 IC is coming or contributed by a current I1 and by a current 2 IC minus I1. So the understanding you should carry at this figure 2 is we are looking at coil 2. Don't forget, sorry, we are concentrating on coil 1. Don't forget that. With respect to coil 1, compared to figure 1, in figure 2 there is a reduction in amount of current. That is what we understand from figure 2. Now this is a second snapshot. That means armature is continuously rotating, and we got a second snapshot of the rotation. Now let us go to the third snapshot. Let us go to the third snapshot. So to look at the third snapshot, let us slightly, so the third snapshot is going to be with the slight shift in the brush position. Okay, that is not slight shift in brush position, slight shift in commutator segment with respect to the brush. So now what we are going to assume is the 50% of the brush width is occupying 50% of commutator segment 2 and 50% of commutator segment 1. So in that case, and don't ever forget, the current still coming out is 2 IC, and current in C2, C3, and this is C2, and now the current is still IC and current here is still IC. But interestingly, this commutator segment 2 offers you say IC at this junction, commutator segment 1 offers you again IC at this location, then 2 IC has come. Now you look at that, if, listen this very carefully, now if this IC is coming from coil 2, okay, and this IC is coming from coil 3, then at this point of time, the very important point is the current in the coil, current flowing through the coil C1 is equal to 0. Coil 1 is equal to 0. In other words, we can say that the coil 1 is short circuited. Coil 1 is short circuited by the brush. When you say the coil 1 is short circuited by the brush, how do you understand? You look at that. The two ends of coil 1 is now electrically connected. Now it is electrically connected through the brush. So it is basically, if you look at the diagram separately, let us say this is my coil 1, okay, and these two sides are just shorted by the brush. You can look at very well from the diagram. So if you look at, if you make a short circuit, basically it means that the induced EMF across this coil becomes 0. The induced EMF across this coil becomes 0. When you say there is no induced EMF in the coil, there is no current flowing through the coil 1. So in that case, at figure 3, so this we can call it as figure 3, we can look at an interesting phenomena, that current flowing through coil 1. And don't ever forget, we are interested in watching the pattern of current in coil 1 only. So the current flowing through coil 1 in figure 3 becomes 0 at this moment. And don't ever forget that still we are retaining the current delivered by the machine as 2 IC in a given brush. And this 2 IC is are coming from C3 and C2. The next interesting part comes in figure 4. So let us look at the figure 4 much closely. So what we are going to see in figure 4 is that, let me mark this as figure 4. In figure 4, yes, I am going to change the position of the carbon brush with respect to diagram, but actually position of carbon brush is not changed. Position of the brush with respect to the commutator segment, or the commutator segment exposed to the brush is changed. So now right now I said that 50% of the brush is occupying 2 and 50% of the brush is occupying 1. Now what we are going to do, it is similar to figure 2 and it is just opposite to figure 2. Similar in the sense the occupancy is not 50-50. That means there is a less portion of brush getting connected to commutator segment 1, and majority of the portion comes to commutator segment 2. Now in this case, the coil number 1 is actually relieved from the perfect short between perfect short. So in that case, if you look at coil 2 and coil 3, that is also important. There is a contribution. There is there is a contribution coming from this commutator segment. Let us call that contribution as I2, and it is very similar to what we discussed in figure 2. Here also I2 is going to be less than IC. So there is a contribution coming from commutator segment 1, but that is I2. And don't forget, still the current getting exit from the brush is going to be 2 IC. Then in that case, in the coil 2, if you look at the current in coil 2, let us say this is still IC, then if this happened to be IC, if that is happened to be IC, and this branch has a current of I2, then in that case if you try to apply Kirchhoff's current law here with the current IC here, you can very well see the current, you apply Kirchhoff's current law at this node, you can very well see that the current which is going here towards the commutator segment is I2, and the current in coil C3 is IC, then this must be IC minus I2. But the very important thing to note here is the current direction in C1. So if you just try to compare the current direction in figure 1, 2 with respect to figure 4, the current direction in the coil number 1 is reversed. Current direction in coil 1 is right now reversed. So what is happening in figure 1? The current direction in coil 1 is left to right with the IC value. In figure 2 it is still left to right, but the current has reduced from IC to IC minus I1. In figure 3 it has completely become 0. In figure 4 some current is appearing, because here it is 0. In figure 3 it is 0, but in figure 4 there is a current started flowing in C1, but it is not equal to IC, it is less than IC, and the current direction is right to left. So let us go further. So in this case the current which will flow towards this, applying Kirchhoff's current law here, that is going to be 2IC minus I2. So if this is 2IC minus I2, so the net current happened to be 2IC here. Now we are going to look at the final figure with respect to the entire process of commutation here. I would say the figure number 5. So let us say this is figure number 5. In figure number 5, again we are trying to do the change with respect to the brush. You can see here, now the brush is completely occupying commutator segment 2. So in figure 1 the brush was completely occupied with commutator segment 1. Now due to the rotation, the commutator segment 2 comes and occupies the brush. So this is coil 3 and this is coil 2. Don't forget that the current which is coming out is still 2IC. Now the current direction in coil 1 would have come to IC in this direction. So this is still in IC and C3 is still IC. Then now if you look at the sum of the current, it is IC plus IC, it is 2IC now. So if you look at the figure number 5, it basically shows that the current direction in coil 1 is just completely opposite and equal with respect to figure number 1. So what we have understood throughout the process can be depicted using a simple figure. The figure can be like this. Okay, whatever we understood throughout our process of explanation can be explained. Just one second. Can be explained using a simple time diagram. Okay, probably I can. Yes. So now what I am going to look at is, let us say this axis represents current current through the commutated coil. What is commutated coil? That is C1. What is commutated coil? The coil experienced a current reversal is called commutated coil. And my x-axis is going to be simply time. So what we have seen throughout is, let us assume this is time t equal to 0, where in the coil 1 the current direction is positive, as well as it is the magnitude is plus IC. Magnitude is plus IC, and the current is maintained at IC. Once the process of commutation started, what happens? The current magnitude is started declining. See, for an example, you can take some instant where this current was IC minus I1. Then it keep declined and it has come to 0. Okay, probably this was our figure 2, and this was our figure 1, and this is our figure 3. Then going further, we had a negative current. Okay, let me draw it neatly, because this is going to be simply straight line. So I think better I can represent this by straight line itself. Okay, so it is going to be like this. Okay, you can have a slight adjustment here. Okay, so this is going to be IC plus IC. At this instant, that current was IC minus I1. Then it kept declined, and very interestingly, we have come across another current. Probably we can project to the negative axis also. We had a current where it was I2 IC minus I2, but don't forget it is a negative value. Okay, that was figure number 4. In figure number 5, we have reached a value which is minus IC. So you look at this figure, the entire coil, the one particular coil. So what are the understanding? The coil 1, which we the commutated coil, which is nothing but C1 undergoes the change in current, magnitude and the direction in a given time. Okay, and that given time, listen very carefully, this period, okay, where the current in a particular coil is from positive and changes to negative, this entire period can be marked as TC. Okay, where the TC is the time of commutation. Okay, it is the time taken for commutation. Okay, so if I correctly plotted as per an ideal commutation, if I correctly plotted this zero crossing, what they are telling, it comes at TC by 2. That means if this is total TC, and this zero crossing will occur at TC by 2. So now whatever we have seen, it is something very smooth, and there is a changeover in the current of a coil 1 from plus IC to minus IC. But the background story is, we can see a coil experiences change in current with respect to time. Now this statement is actually looking interesting, because the coil is experiencing change in current, right? This is what I can write mathematically. So if at all that particular coil find an inductance, then naturally there is an EMF, there is an induced EMF. That induced EMF is basically going to oppose the process of this commutation. Okay, that means we know that as per Faraday's law, any induced EMF happen to be, say, self-induced EMF, and that will oppose the cause. Now the cause is the reversal of current, correct? I mean, the reversal of the current, how quickly it happens, that is a cause. So what is interestingly given in the literature is that because of this rate of change of current experienced by the coil self-inductance along with this rate of change of flux would cause an EMF. That EMF, since it is opposing the process of commutation, it will make a delay or delayed commutation. It will try to make a delayed commutation. What is delayed commutation? Let me tell you that, okay, it is good, you started plus IC, and we have to reach minus IC. But what happens, this may happen in a way like this. It may happen in a way like this. What do you mean by that? It means that the zero crossing of current, you look at this, the zero crossing of current is getting delayed from an ideal commutation process. Instead of saying ideal commutation, the textbook says that this is a linear commutation. This is called linear commutation, and this is marked as delayed commutation. It's marked as delayed commutation. So the delay, I have explained the reason for why there is a delay. Okay, let that be delayed. So what is getting delayed? Zero crossing of current, or the coil current becoming zero is getting delayed. It means, don't ever forget this, it means that you look at this portion, because of this delay, though the time of commutation, listen carefully, this is my TC, correct? What is this exactly? TC is, this TC also represents the position of commutator segments with respect to the brush. The TC is also represents the time taken, the traveling time of the commutator from one place to another place. I mean, that can be explained here. Listen carefully. See, in this figure, I can very well see that the brush which delivers to IC is 100% occupied with commutator segment 1. Now let me show you the next figure. Let me show you the very next figure. In the very next figure, I will modify this brush position as this way. That means the brush is completely occupied at which position? Commutator segment 2. So the TC whatever we discussed is again the physical position change of 1 and 2 with respect to brush. So complete occupancy of 1 under brush is, let us say, T equal to 0, and complete occupancy of commutator segment 2 is T equal to capital DC. Alright, and don't ever forget that in the entire process, in this, the current coming from 2IC is coming from where? Coming from this coil as IC, this coil is as IC. This is IC, this is IC, and this is also IC. That is what we looked at in time t equal to 0. In time t equal to TC, what is actually expected is that this is still IC, okay, and this coil 1 is also expected to be IC, but look at the delayed commutation. At TC. Okay, this is TC, don't forget. Okay, this is TC. At TC, you can still find a current which is less than IC. Let me call that as IC minus I. So ideally at TC, we are trying to see a current minus IC in coil 1, but because of delayed commutation, which is delayed commutation, the dotted line represents the delayed commutation. Due to delayed commutation at TC, that means the commutator segment has completely occupied the brush at TC, where you expect the current in the coil 1 is minus IC, is not IC, and it is not minus IC, it is minus IC minus I. It means, suppose if I mark this current as IC minus I, this current still happen to be IC. What is that current which is coming from here? It is just going to be 2IC minus I. Look at this, 2IC minus I. Then, but what is the current which is asked by the load? 2IC. So the rest of the current, what is the deficit current? Deficit current is I, correct? So that tries to come out from here, tries to come here, but we do not have any electrical connection. So that particular current trying to reach this brush, which is nothing but I, through air, and a current flows through air and reaching the brush makes sparking. Okay, look at an interesting phenomena. Ideally speaking, okay, so we have to recollect, it is better to recollect. Ideally speaking, the linear commutation process will make sure that plus IC current in coil 1 at time t equal to 0 and at time is equal to TC, where the commutator segment 2 completely occupies the brush, then it is expected to be minus IC. But due to the change in current experienced by the coil and its by own self-inductance, the declinement in the coil current would cause an EMF, and that makes the commutation to be delayed. Then if you call it is a delayed commutation, the current which supposed to come to minus IC is not coming as minus IC at time TC. It is still lesser than that. It is reaching minus IC little late. So because of that, though the brush has completely come to the position of 2, but the current supplied by the coil 1 is still IC minus I, and the coil 3 try to supply IC. So the total current trying to come out from the commutator segment 2 is simply 2 IC minus I, but the load tries to draw 2 IC from the machine. Then naturally there is a small excess current which is trying to come from this portion to satisfy this load current, and that naturally jumps from commutator segment towards the brush through air, and that jump through the air causes sparking. So what I want to conclude here is, this is the electrical reason, this is the electrical reason behind the sparking at the commutator. And very interestingly, that sparking happens at the trailing edge, of the trailing edge of the brush. Okay, so probably in our physical class we will look at, is there any mechanism to sort out this problem? I mean, it means is there any mechanism to reduce this spark? So in the entire video we have kind of clearly seen that how a commutation process happen. It means how the current reversal in a coil happens in an armature winding. Then we had looked at the delayed commutation and what is linear commutation, and due to delayed commutation why there is a spark in the commutator and brush arrangement. Okay. Thank you. See you.